So our next speaker is Mitsuhiro Nishida from Gwangju Institute of Science and Technology. He will talk about reflective entropy and entanglement wedge cross-section with the first order pressure. Please.
Thanks for introduction and thank organizers for giving me the opportunity about this talk. I'm Mitsuhiro Nishida, postdoc at Gwangju Institute of Science and Technology, Korea. So today I would like to talk about the holographic duality between reflected entropy and entanglement wedge cross-section. We explicitly compute and compare their first order direction. This work is collaboration with Nishida and first, I start to explain entanglement wedge cross-section. As explained in yesterday's Koji Miyamoto's talk, this entanglement wedge cross-section is the minimal cross-section in entanglement wedge. Now, this entanglement wedge is the gravity dual of a mixed state OAB. For example, for reduced density matrix OAB, entanglement wedge is this blue shaded region bounded by two red minimal surfaces. And for thermal state OAB, entanglement wedge is this blue shaded region outside the black hole horizon. And area of this dotted line is this area of this dotted line corresponds to entanglement wedge cross-section, and this surface divides the entanglement wedge into left part is A and right part is. And there are some proposals of the dual quantities for entanglement wedge cross-section in the field theory side, such as entanglement of purification, logarithmic negativity, entropy, and effective entropy. Today, I will focus on this reflected entropy. Okay, so reflected entropy, this SR, is defined by entanglement entropy of a canonical purification, OAB. Okay, as an example, consider this mixed state OAB to this. And by interpreting this, this class as vector on Hilbert space HA star and HB star, we can define square root of OAB, and this is a pure state of this Hilbert space. This Hilbert space HA times HB times HA star times HB star, like this. And this construction of pure state is called as canonical purification. And by using this pure state, this effective entropy is defined as this. In other words, this effective entropy SR is the entanglement entropy of this prefined state. And in this paper, they propose the holographic duality of this effective entropy and entanglement wedge cross-section. Moreover, this holographic duality is generalized by a replica index M. Now, this SMR is the effective entropy with a canonical purification of M's power of. And this BMW is the entanglement wedge cross-section with the gravity dual of M's power of. Generally, explicit computation of this duality is difficult because explicit construction of the gravity dual of M's power of OAB is difficult, as known in the computation holographic many entropy. So our motivation is that we want to check and understand this relation by a simple example. This is our motivation. Then I will explain our result. We explicitly check this holographic duality for duality in the 2D holographic CFT and entanglement edge cross section in this geometry up to the first order n minus 1.
Is it how many integer or half integer?
Sorry, this m.
Yes.
Now we consider analytic continuation, and so this m1 minus is very small quantity. And this c is the central charge, and this z is the cross relation, depends on the position of two intervals, and this gn is the gravitational constant. And comparing between this zeroth order was checked in the original paper. And our new result is computing and comparing this first order terms. And they are exactly matched with this well-known relation between central charge and gravitational constant. Okay, so next I will review the holographic duality between reflected entropy and entanglement edge cross section by assuming the duality between thermal state and black hole. In particular, I will explain the meaning of this factor. Okay, so then to explain the duality between duality for entanglement cross section, I will start to explain the duality between thermal field W and two-sided ADS black hole. Okay, let's consider thermal state of this Hilbert space like this, and assume that this thermal state has a gravity duality such as one-sided ADS. And from this given thermal state, we can define thermal field W. And this is the pure state of HAB times HAB star. And this pure state is a canonical purification of this thermal state. And Malgasner proposed that this thermal field W has a gravity duality such as two-sided ADS. And this red circle is the black hole lines. And this two-sided ADS black hole has two boundaries, left boundary and right boundary. And this two boundary correspond to this thermal field W is a pure state of HAB times HAB star. And as explained in the previous slide, reflected entropy of thermal state OAB is entanglement entropy of canonical purified state, which is thermal field W. And since this thermal field W has a gravity duality as two-sided ADS black hole, so reflected entropy of thermal state corresponds to holographic entanglement entropy two-sided ADS black hole. And these two dotted lines correspond to the minimal surface, and this minimal surface divides the two-sided ADS black hole into upper part with A star and lower part with B star. So reflected entropy corresponds to the area of this minimal surface because of this relation. Since this two-sided ADS black hole is the double copy of one-sided ADS black hole, area of this minimal surface is 2 times area of this entanglement edge cross section. So we can obtain the holographic duality between reflected entropy and entanglement edge cross section. In particular, this factor 2 comes from the double copy for canonical purification. Or in other words, this two-sided ADS black hole is the double copy one-sided ADS. This is a meaning of 2. finally, I shortly explain our computation method of reflected entropy and entanglement edge cross-section up to the first order n-1. Okay, so first let us remind our target. We are interested in the collegiality between SMR and EMW, where this SMR is the defective entropy. Defective entropy with a canonical unification of nth power wave. And this EMW is the entanglement wedge cross-section in the gravity-dual nth power wave.
I see. So your M is M divided by half in focus angle, right?
Sorry.
Your M is the M over half, over 2, right?
No, I think this I think
Because canonical purification, you have to set M equals to.
yes. So in canonical purification, so we need to consider even M, but now we consider analytic continuation to consider very small m-1. And I think m equal 1 corresponds to canonical purification.
Yeah, that's what I'm saying. You first take an M power and then take a square root, right?
For example, I think like this.
Yes.
Yes, but now m corresponds to m's power to this already. So then, if we consider m equal case, purified state becomes m over 2 power. Then, to understand this duality, explicitly we studied the first order correction n-1. Okay, first I will explain how to compute SMR. As same as the computation of entanglement entropy, this SMR can be expressed as a partial integral of this replica manifold or correlation function of twist operator. And this replica manifold depends on two replica index n, and also these twist operators depend on two replica index m and n. And in the 2D chromatic CFT, this 4-point function can be approximated by a single conformal block. And a perturbative expansion of conformal block is studied in this paper. So we use the perturbative expansion, perturbative formula in this paper. So to compute this SMR in this SMR. Next, I will explain how to compute this entanglement wedge cross-section. In this paper, the gravity dual of m's power rho AB. And in this paper, the author proposed that the gravity dual of m's power rho AB includes the back reaction from cosmic planes. In particular, we need to change this red surface, red luminous surface by cosmic plane with non-zero tension. And at the first order m-1, the author of this paper computed the first order correction area of this red surface. And we can apply his computation method to compute the first order correction of this area. Then by this application, we can compute this entanglement wedge cross-section. So by using these computation methods, we can compute SMR and EMW as follows. And as you can see, these first order terms are exactly matched with this real relation between central charge C and gravitational constant G. And this correspondence means an explicit check of the collegiality between reflected entropy and entanglement wedge cross-section. In the first order n-1. So this is our result. Then let us summarize my talk. So we study the collegiality between reflected entropy and entanglement of edge cross section. We explicitly compute and check this duality up to the first order in minus 1. That's all. Thank you.
Do you have n minus 1?
Sorry.
The other n minus 1.
No, sorry. We consider n equal to 1 limit, and we don't consider the back reaction from this entanglement.
So if you do, what daily trivial fractions?
I think one problem is computation of back reaction from this entanglement cross section is difficult, at least for analytically. So I think computation of first order in n-1 may be difficult. I think it may be difficult, but now I think it is also interesting problem.
More questions, comments? If not, let's thank Mitsuhiro again. So this is the end of today's program.